Hello student, hope you are doing well. Today we are going to solve one step bar problem using Ansys 14.5. The problem is solve the problem using Ansys. A step bar is as shown in figure. One end of step bar is fixed and 15 kN force is applied at other end. Determine the nodal displacement and stresses in each cross section and reaction forces. Now this is the diagram is given. This is our first element and this is our second element. First element area is 200 mm square, second element 100 mm square. First element's Young's modulus is 200 gigapascal, second element 150 gigapascal. Then Poisson's ratio for first element 0.3 and for second element 0.27, and if length of the first element, that is 200, and it is 150 for the second element. Now after solving this, we will get the displacement at node 1 is equal to 0 mm, displacement at node 2 is 0.075 mm, and displacement at node 3 is 0.225 mm. Again, the reaction force at node 1 is minus 50 kilo Newton, and stresses in element number 1 is 75 Newton per mm square, and stresses in element 2 is 150 Newton per mm square. Now if you see the solution of this problem, so we can see here, so this is our problem and we solve this. So this is the finite element physical model. This is element number 1, 2. Element 1 is connected with the 1 and 2 node. Element 2 is connected with the second and third node, and this is the force. Now we find out the first stiffness matrix K1. After that we find out the K2. Then we find out the assembling global stiffness matrix, that is K. And as we know, the stiffness, displacement and force global matrix relation is K into D is equal to F. So if we see, so displacement 1 at node is 0, D1 is 0 because node 1 is fixed, and force is applied only at third node, that is 15 kilonewton. So F1 is 0, F2 is also 0. If you put this equation in this and if you solve this, so we will get the displacement at node 2, that is 0.075 mm, displacement at node 3, that is 0.225 mm. Again, if you determine the reaction forces, so we get the reaction forces at 1 is minus 15,000 Newton. Now again we calculate the stresses. So in stresses in element number 1, so this is the formula. If you put the value inside this E, L and D1, D2, so we'll get the stress 1, that is 50 Newton per mm square. Similarly, with this we can calculate the stresses in element number 2, that is 150 Newton per mm square. Now we are going to solve this problem using Ansys. Now we start the solution. We start with preferences, select structural analysis. Okay, in preprocessor we have to select element type, add element. Here we have to add link. Click on the OK. Close this. Add real constant. Add this. Add. So this is our link. Okay. So we want first element having cross section 200 mm square. Say OK. Again we want to add this. Select this. So you have to add for the second element a real constant number, say 2, so that is 100 mm square. Say OK. Close this. Now next we have to add the material properties. So in material model, so we are going to structure analysis, linear, elastic, isotropic. So material, our first material is 200 gigapascal, so 2E3. And what is Poisson's ratio? Poisson's ratio is 0.3. Say OK. Next again we have to add the material number 2 for second element. So material new, define material ID 2, OK. Isotropic material, and it has 150 gigapascal, 150 E3. Newton per mm square, and Poisson's ratio is 0.27. Say OK. Close this window, make a save db. Next, now we have to create the modeling. So modeling, create. So create nodes in active coordinate system. So we have to select the first node, its coordinate is 0 0 0. Second node, its coordinate is 200 x 200 y 0 z 0. Apply. And third, its coordinate is 350. Say OK. Now three nodes are generated. Now save, make it save db. Now next is, now we want to add the element. So in element we will say element attribute. For material link 1 we are going to set here material 1, real constant 1. OK. This element is through nodes from this point up to this. Say OK. Now this element is generated. Now again we are going to generate second element. This is second material is there, and second real constant. OK. Through nodes from this point up to this. OK. Now if you want to see this cross section, control, plot control, in that style is there, size and shape, click this OK. OK. Now it is still not visible, so you make it multi-plot. Now it is visible. Now preprocessor, now last step in the preprocessing we have to apply the load. So in load we are apply structural displacement. So displacement at node, this node is 0. Say OK. So all degrees of freedom is 0. Say OK. Next is we want to apply the force at node number 3. So force on node. So here we want to apply the force. So our force is 150. Say OK. So fx direction, and that is 15 kilonewton. So 15,000 Newton. Say OK. Now this force is applied. Now save this. Now we are going to do the solution. In solution, solve current ls. OK. So solution is done. Close this window. Now we are going to see the solution. In solution, okay. Now we are going to see the post processing. In post processing, we will see the plot, deform, undeformed shape. Say OK. So you can see maximum deformation is 0.25 mm. Okay, so this is deform and undeformed. Again, if you see nodal solution, if you see the nodal solution for stresses, we will select this stress. In that von Mises stresses, OK. So you can see 150 is maximum stress and 75 is minimum stress. So our solution is exactly match. So this is 150, it is maximum, and 75 is minimum. And displacement, maximum displacement is 0.225 mm. Now if you see the values, so in list result you can see nodal displacement, nodal solution, this degrees of freedom in x direction. Say OK. You can see here. So this is our displacement. So first node 0 displacement, second node 0.075 mm displacement, third node 0.225 mm displacement. Again you can see the reaction solution. So reaction solution for all items, say OK. So reaction is generated at node 1, so that is minus 15,000 Newton. So that is negative. Again you can see the animation of this. And if you want to see the stresses, so in nodal solution stresses, so you can see the values on Mises stresses. OK, you can see the value. So how stresses are generated. minimum, okay, and maximum value is 150 Newton per mm square. Now if you want to do the animation, you can do the animation also. Deform on deform shape, say okay, deform on deform, okay. So this is the animation. So we'll close here. If you want to plot this result, so plot. So here you can see here style, colors. So you can see here, so this is the reverse colors. Okay, you can take print screen also. Similarly, you can see the contour plot of nodal solution stresses here. Okay, our axis minimum stress is 75, maximum stress is 150 Newton, and maximum deformation 0.25 mm. Okay, our answers are matching with the our analytical solution is matching with our Ansys solution. So thank you.